The law of independent assortment states that the inheritance of each gene is going to be an independent event. So since each gene is an independent event, this is going to enable us to use the multiplication rule for multi-gene crosses. And so if we want to look at more than one gene at a time, the monohybrid crosses are pretty easy to do and they have a really small Punnett square, just 4 boxes. But when we do start talking about dihybrid crosses, the square can get up to 16. If we start talking about trihybrid crosses, so 3 genes at a time, it gets even larger. And then we could go on and on. So we do want to be able to use the probability rules so that we can avoid using those really big Punnett squares. And so if we look at an example here, so if we had this cross, for example, and we wanted to know what is the probability from this cross. So what is the probability of, I'm going to say, this particular offspring? So we want to know, what is the likelihood of getting that? Well, one approach would be to go and draw the big Punnett square and then just go through and count up how many of the boxes actually match up with that particular genotype. Another way to do it, and a much simpler, faster way to do it, is to use this multiplication rule. Because what the multiplication rule is telling us is that what happens with the A's here is going to be completely independent from what happens with the B's. So we can really separate this. So this is the key. We're going to separate this into 2 monohybrid crosses. So we're going to have a little cross that we look at the A's, and then we're going to have a little cross where we look at the B's. So let's do this first. So let's take a look at that. If we look at the A's, if we have one parent here that's heterozygous and another one that's heterozygous, if I just write this down here, this is the cross. And if we wanted to know over here, what is the probability of getting heterozygous offspring from that? Well, I can draw the small Punnett square. And so if I do that here and fill it in, what I can see from my square is that half of the boxes, so right here and here, they do match what I'm looking for. So I'm just going to come over here and write 1/2. So 1/2 is the probability that from these 2 parents, I'm going to get this combination of A's. So it's going to be heterozygous. Then what I want to do is I want to look at my other monohybrid cross, which is the B part of it. So if we look at the B part of it, both of those parents are also heterozygous. So I'm going to write that here. And I can draw the little Punnett square for these parents. And so if I fill in that square, what I can see is that if I'm looking for little b, 1 out of 4 is going to match that. So I can put 1/4 as my probability for my little b's. Then all I have to do is go through and multiply this, and I get 1/8. So that is the final answer. So 1/8 of the offspring should have this particular this particular genotype to them. So 1/8 of the offspring should have this particular genotype to them. If you wanted to double check this, you could go and draw the big Punnett square. So with the Punnett square, we do have a total of 16 boxes if we're looking at a Punnett square for this particular cross. So if there are 16 total boxes, 1/8 of them should have this, which means that you should be able to find 2 boxes in that big Punnett square that do match up with this particular genotype. So obviously a much faster way of doing this than filling out that whole Punnett square. So if we look at another example, here you can see that we've got much bigger genotypes that we're looking at. And we have really 4 genes that we're analyzing. We have an A gene, B, C, and then D as well. And so we want to predict what is the probability, I'm going to say, of getting an offspring that looks like the dominant version of all 4 genes. So in other words, we want it to look like big A, big B, big C, and big D. And that really is what the two parents look like, even though they do happen to have different genotypes. So notice that what we're saying here is that we are looking for a particular phenotype. And so the first thing that I would suggest that you do is you write down what it is that we are really actually looking for genotype-wise. So if we want it to look like big A, what we're saying is that we want it to have at least one big A. And we don't really care what's in the second position, because regardless of what's there, it is going to have that big A look to it. We also want it to look like big B, which this would be what we need for big C again, and then also for D again. So this is our combination that we're looking for. And we know that what happens with the A gene is going to be independent from what happens with the B, the C, and the D gene. So we're going to break this into 4 different monohybrid crosses, since we are looking at 4 genes at a time. So let's go through and do that. So if we look at the A gene first, and I'm going to write my A information over here in red, and I'll write it up here over on the side. So notice that both of my parents, we need to look at their specific genotypes. So I have one that is heterozygous for A, and I've got one that's homozygous dominant. So when I do the Punnett square for this, in this particular scenario, what you'll find is that really every single one of these happens to be matching this thing that we want here. So every single one of them is going to look dominant for A. So the way that we would write that is that our probability of getting a big A look is going to be just 1, or 100%. So that's my probability for the A's. If I look at the B's, and I'm going to write that in green here so we can keep them all straight, the B's, both of them are going to be heterozygous. So here are my B parents, and I can go ahead and draw that small Punnett square for the B's. So after I get that Punnett square drawn, I want to look at the boxes and say, what is the probability of getting this? What is the probability they're going to look like big B? And we can see that we do have 3 out of the 4 boxes that are going to match that. So that would be my probability for B. If I then go and look at C, we have one parent that is homozygous dominant, and we have one that is heterozygous. So here is my C Punnett square. And so once we get this filled out, we evaluate the probability that they're going to look like capital C. And we can see that in this case, actually every single one of them does. So that's another 100%, or 1 is the way that we would write that. And then if we look at the last one, D, we've got 2 heterozygous D parents. And so here is my cross. Again, draw the little Punnett square. And then we would evaluate what we end up with in the boxes. So once we do this, when we evaluate it, we do have 3 out of the 4 that do have the capital D look. So I'm going to write that right here. So that is really the foundation of this, because now we have figured out the individual probabilities for each gene giving that particular look. And since they're independent events, we can multiply them together or multiply directly across. So I'm going to do that, and I get 9/16. So that would be my final answer here. And that tells me the probability that when I do this cross, that I'm going to get an offspring that looks dominant for every single one of the genes involved. So for all 4 of the genes.